2022 has been another banner year for the PV industry, with global demand expected to creep towards 250 gigawatts. The milestone of 1 terawatt of installations has been surpassed globally, and the second terawatt is just around the corner. But as solar and energy storage moves onto the main stage, a new set of responsibilities are being encountered, not least among them how the industry will continue to grow with the current levels of energy and material consumption. My name is Jonathan Gifford. I'm the editor-in-chief of PV Magazine Global, and welcome to this PV Magazine webinar. Our webinar today is being delivered in partnership with Trina Solar, and the title is Entering the Terawatt Age, a 360-degree view on solar sustainability. It's a big issue, and it's taken on major prominence over the last 2 or 3 years. There are many different aspects that make up sustainability, and they really used to be a kind of nice to have in the solar industry, and that was the case up until very recently. But there's a renewed focus on supply chains. There's a focus on environmental, social, and governance, or ESG, from an investor perspective. And there's an emerging need to tackle material and energy resource consumption while the solar industry scales. And all of these have made sustainability a pressing concern. In fact, it's increasingly a holistic approach to sustainability that's becoming a must-have in solar and energy storage. And we have presenters today on this webinar that can give us 2 pretty unique and important perspectives on solar sustainability as we head towards this terawatt scale, one from the research community and the other from the all-important standpoint of a manufacturer. Pierre Verlinden is the managing director of consultancy Amrock and has experience in PV research dating back a number of decades. Pierre's held leadership roles at leading companies like SunPower and Trina Solar and is currently an adjunct professor at the UNSW. He is on the board of technology companies like Oxford PV and BT Imaging, and in 2019 was awarded the Becquerel Prize for his contribution to PV research. Adele Schau is the head of product and marketing for Trina Solar Europe. Adele has been with Trina since 2009 in China and in Switzerland. She's worked in a number of different roles, including as a certification engineer, global product manager, and in marketing and managing a number of solar products, including the integrated PV power plant system, Trina Pro. Adele and Pierre, welcome today.
Thank you.
Thank you. Good morning. Good
Wonderful.
morning, Jonathan.
And we're going to have presentations from both Adele and Pierre, and they're going to join us for a Q&A round a little bit later. So please, I ask you to get involved and send through your questions at any stage throughout this webinar. Please do get involved, and we'll have a great discussion to round out the event. Adele and Pierre, I'll see you very shortly. But before we begin the presentations, you might be joining a PV Magazine webinar for the first time. So first of all, welcome to you. And here's some information about how you can get involved today. Please feel free to send through your questions, as I said, at really any time. I'll be keeping a track of the questions. I'll get back to you if I feel I need a bit more information or a clarification, and I'll be putting those questions directly to Pierre and Adele, both after their presentations and also in the quick-fire Q&A round. So I encourage you to get involved with all of your solar sustainability questions, whether that's right across the gamut of solar sustainability or indeed energy storage also. And if you experience any tech problems, we know that can happen when you're attending a webinar. You can get in touch with our webinar team at any time. Just send a message via this big marker platform. Our behind the scenes team are standing by to help. One quick tip, a very easy way to fix up any technical problems is simply refresh the browser. It really does sort a lot of things straight away. One question we always get when we host a webinar here at PV Magazine is, will there be a recording, and will the presentations be available after the event? Well, I have good news. That's a yes to both of those. There'll be a recording of this webinar posted online, and you'll receive a link also to that recording that you can share with friends, with colleagues who weren't able to join us live. Well, I think that's enough from me at this stage. Let's get stuck into our presentations. As I said, Pierre Verlinden is the Managing Director of Amrock, based in Australia. Pierre, you've really driven this conversation about sustainability in solar. In fact, it was a presentation when you were receiving the Becquerel Prize back in 2019, I think, that was really crucial in spurring this discussion about how we are going to achieve a sustainable solar industry at the terawatt scale. So I think it's really fitting we have you here on the event today. I'll pass the floor over to you.
Thank you, Jonathan. And yeah, I remembered actually the first presentation I did about possible issue with material sustainability was in 2013 at the UPV-SEC in Paris. But of course, that probably disappeared in the memory of most people. But here we are. It's true that it's one of the topics that keeps me awake at night sometimes, and I'm wondering how we're going to do this. So sustainability of PV manufacturing at the multi-terawatt level. So the first question, and I need to find out how here we go. So why are we talking about sustainability for the moment? Well, PV electricity is clean. It should be sustainable, right? PV is used to be about costs. So it used to be discussing about cost efficiency and reliability. And if it's reliability and cost effective against fossil fuel, it should be sustainable. PV in operation does not use any consumable. It should be sustainable. And all those questions, why are we talking sustainability today? It's because PV will be huge, will be enormous. And let's put things in a context. Right now, we are in the epoch, the geological epoch that we call Anthropocene. It means that it's a period during which human activity has been dominant to influence climate and the environment. And people put that the beginning of the Anthropocene at the beginning of the Industrial Revolution, so around 1780, when the steam engine was invented. Of course, this is just an idea. It's not been officially recognized. It's not an official name for the current epoch, but that's what we call it right now, because we realize that human being has a strong influence on the climate. So if we want to fulfill the Paris, the COP21 agreement of 2015, we were in 2015 allowed to burn only 800 gigaton of CO2, then zero. That is basically the envelope that we have, the budget of CO2 that we have, and that we cannot go over that. Now, if we want to reduce the delta T, the average temperature increase to 1.5 degrees, we have only 400 gigaton. And as you could see, we are already in 2022, and we already have used quite a bit of that CO2 budget. So things are getting very, very difficult, and we need to act urgently to modify our behavior. So a lot of people have done simulations of what we should do and how fast we need to reduce the CO2 emission. And as you could see in those different simulations here with different colors, only the blue one is capable to maintain the excursion of temperature to about 1.5 to 2 degrees C. And so that means that by 2055, roughly about 2050, 2055, we need to reduce to zero CO2 emission. And after that, we need to remove CO2 from the atmosphere. So it's a big task. And so our vision is that the world needs to be 100% renewable, and PV plays a very, very important role. It's probably the largest source of electricity in the future. And to do this, we need to install something like 70 or 80 terawatts by 2050. Of course, with wind, hydro, geothermal, biomass, all of that being linked and interconnected, we will power the entire economy, including the industry, including transportation, including heating and cooling of building, and generation of synthetic fuels to power the rest of the economy, including the industry that requires hydrogen, for example, to make steel or to make aluminum, etc. Now, if we look at the PV production rate and the installed capacity over the last 70 years, what we see is that the capacity and the production rate have doubled every 3 years. It took 70 years to deploy the first terawatt, and it will just take 3 years to install the next one. In 2022, PV generates about 4.5% of global electricity. In 2026, PV will generate worldwide more electricity than nuclear energy. And so this is an example of what we need to do. In blue, you have the cumulative installation of photovoltaics. In green, you have the production rate. And in red here on the graph, you have the annual growth. What we need to do today is continue growing PV at about 25% per year till about 2035. And then we need to stabilize production in roughly about 3 to 3.5 terawatt annually. And this will allow to grow the cumulative deployment to about 70 or 80 terawatt by mid-century without creating a downturn, because at some point, of course, the deployment will saturate and the industry will start replacing the module that have been installed 25 or 30 years previously. So we need to stabilize production about 25 years or 30 years before it saturates, so before mid-century. So when we talk about sustainability, there's different ways to look at sustainability. First, we could look at energy. How many kilowatt hours are consumed per kilowatt peak installed? And that including the manufacturers, the transportation, installation. What's the energy payback time? How fast can we grow this industry to make sure that we don't consume more energy than we generate? Now, we could look also at CO2 emission. What's the amount of CO2 embedded in the modules and how much it is per kilowatt hours? We could look at water and chemical consumption. And we could look also at solid waste, gas and liquid effluents, at the pollution we create. We could look at the material usage. Are they available? What's the scarcity of this material? Is there a risk of price increase, speculation? How is the supply chain? Do we need to recycle or capture valuable material? And also, what is the financial sustainability of the industry? Can we generate enough earning to grow, to build a new production line? And there are different factors that will impact the sustainability. Well, reliability, of course. If the module lasts 1 year, we need to produce a lot more module than if they last 30 years. And so it's very important that we increase the lifetime of modules on PV system in general. Efficiency, performance ratio, annual irradiance, orientation, partial shading, all of those factors impact the amount of kilowatt hours per kilowatt installed. And of course, that impact the sustainability of the industry. Energy yield, do we use bifacial modules or not bifacial module? Do we use tracking or no tracking? All of that will, of course, impact the energy yield and will impact the sustainability. Okay, so if we look at the life cycle of a system, the cumulative primary energy demand, CED, is the sum of all the energy that is being used during the whole cycle of the lifetime cycle of the system. So if we look at the graph under at the bottom of the slide, you see we start with raw material. We process those materials before we manufacture the modules. Then we transport and install those modules, and they are in operation for quite some time. after 25, 30 years, hopefully maybe 40 or 50 years in the future, the system is decommissioned and it's recycled. So each of those steps requires materials and energy and will create effluents. At some point, recycling will generate material that could be recycled and sent back into the chain. So what's the energy payback time? Well, the energy payback time is the total amount of energy, of prime energy demand during the whole lifetime cycle, divided by the energy that is generated by the system, minus the energy that is consumed by operation and maintenance. Of course, CED is primary energy demand, and so we're talking about coal and oil and gas, and the grid is not 100% efficient, whereas we produce electricity. So if we compare the primary energy demand and the electricity generated, we have a ratio of corresponding to the grid efficiency. In other words, when we produce 1 kilowatt hour with PV, we actually retire 3 kilowatt hours of coal or gas. And that's because the grid efficiency is about 30%. So we need to divide that by 30% to calculate the energy payback time. And as you will see in a slide later, the energy payback time of a system is in the range of 1 to 2 years. What is the energy return on investment is the ratio of the system lifetime, for example, 30 years, divided by the energy payback time, for example, 1.5 years. So that will be 20. The energy return on investment is roughly about 20 for PV modules. And that keeps growing over time. But this is, for example, a calculation done by Vasilis Ftenakis, who's an expert in life cycle analysis, and showing the energy payback time of multicrystalline silicon PV or monocrystalline silicon PV or cadmium telluride. That is for the modules, including frame and balance of systems. The second graph at the bottom shows the amount of greenhouse gas per kilowatt hours. If we look at the monocrystalline modules, roughly about 20 grams of CO2 per kilowatt hours. And if you add the balance of systems and the rails and the racks, etc., it will be about 30 or 38, about 28 gram of CO2 per kilowatt hours. And you could compare that with the other method of generating electricity, for example, coal, which has more than 1,000 grams per kilowatt hours, or gas that has roughly about 760 grams of CO2 per kilowatt hours, or nuclear, which has roughly about 24 grams of CO2 per kilowatt hours. So how fast can we grow the industry? Basically, what we want to be sure is that your return on the investment is greater than 1 and much greater than 1. Okay, and this is the graph on the right-hand side shows you an example, the comparison of the energy return on energy invested for different technologies. And you see the renewable energy is growing because we improving the lifetime, the reliability, and we reduce the energy consumed to produce it. Whereas other technologies like oil, for example, the return on investment is reduced because as we start to deplete the resource of oil, it's more and more difficult to get the next barrel. We have to spend more and more energy to extract oil. Now, how fast can we grow? Well, basically, it's the maximum growth rate is smaller than 1 over the energy payback time. So if it takes 1 year to pay back the energy consumed, you could grow for 100%. If it takes 2 years, you could grow at 50%. If it takes 3 years, you could grow at 30%. So you see that the energy payback time, it's important to decide how fast we can grow sustainably the industry. Financial stability. One important thing is that the PV industry ability to grow is limited by the EBITDA. EBITDA means the earning before interest, tax, depreciation, and amortization. And it's limited by the capex. So if you take the equation in yellow here, you say the grow is limited by the average price divided by the capex times the EBITDA. That means that if you have typically an EBITDA of 15% in the industry, and you have a current asking price of average sales price of 26 cents per watt, and your current capex to build a new factory that includes from MG silicon to modules, that's roughly about 18 cents per watt. So the maximum sustainable growth is about 22%. So it's a very important factor, because for the pretty much it's the first time since the industry started 50 years ago, is the first time that the industry is capable to grow with the money it earns from the business. And this is mostly due to the fact that the capex is reduced regularly, and this is the red line in this logarithmic plot that represent the cost of, for example, in a PERC cell production line, it reduced by a factor of 2 every 3 years, and mostly due to the increase of throughput of the different tools that compose that manufacturing line. So when we buy a 400 watt PV panel that costs about $100, it will produce exactly the same amount of electricity as 6.9 tons of coals. So that costs about $280 US. So that shows you directly what the potential of sustainability of the PV industry. And this is represented by the graph on the left-hand side, with 1 terawatt of PV system consume about 3 times 10 to the 17 joules in primary energy demand. It will consume about it will generate about 698 million tons of CO2. But in the same time, it will save 25 billion tons of CO2, and it will save 3.9 to 20 joules in primary energy, and will generate 22,500 terawatt hours over 25 years. So to give you an idea, yes, we do consume energy. Yes, we do generate CO2, but we save a lot of CO2 and we save a lot of primary energy by operating PV panels and PV systems. Now, let's talk about material sustainability. You see on the right graph, the right side of the slides, you see a graph of the cost of manufacturing versus the cumulative production. And it's pretty much a straight line in that logarithmic plot. And that represents what you probably have heard, the learning rate. And you could see the learning rate of silicon, it's roughly about 24%. Now, you see a bump there, roughly around 2010, when the cumulative production was about 10 to the 4 megawatts. And that bump is due to supply constraints. At that moment, we were constrained in the supplying of polysilicon, of purified polysilicon. And that lasts a few years. So bumps on the learning curves are usually generated by supply constraints. Supply constraint could be due to the inability of suppliers to grow as fast as the demand, to grow as fast as the industry. And so, for example, in 2005, 2010, the polysilicon industry could not supply the purified polysilicon as fast as the PV industry was growing. And recently, we have seen also some interruption of supply due to fires and flooding For example, there were several polysilicon factories that got into fires, some flooding in China that interrupted the industry. We had also COVID, for example, that prevent the supply to reach the manufacturers. But there is also those inability, those supply constraints that I mentioned, 1 and 2, are temporary. They will be solved at some point. However, number 3, material scarcity is another problem. So, for example, material like silver, indium, bismuth, tellurium, cadmium, etc., materials that are pretty rare compared to silicon, and we have to make sure that we have enough of those material in the future when we reach the terawatt or the multi-terawatt level. The graph on the left side shows the material that we should not use in photovoltaics. The one that are below the blue line there are 7 order of magnitude in terms of abundance compared to silicon. And those materials we should not use in photovoltaic because at some point as we grow, they will not be available anymore. And those materials are silver, indium, palladium, gold, of course, and platinum. Of course, we know all of that, but also bismuth and cadmium and tellurium. We should not use those materials. This graph on the right-hand side actually showed that graph in 2013, as I said, at the EU PV-SEC in Paris in 2013, and showing a simulation of the impact of the PV industry. That's the blue line here that become dominant about 2020. And by 2020, we see that PV is actually growing the demand for silver. It's the fastest growing demand for and usage for silver in the industry. The world production of silver is about 30,000 tons per year. You say we could recycle, of course, but recycling does not become significant until 2050. If we recycle today, we recycle the module that have been installed 25 or 30 years ago, and the quantity of those modules are not sufficient to supply silver for the industry. At 3 terawatt level, we need to reduce the usage of silver to less than 2 milligrams per watt. Currently, we use roughly about 20 milligrams per watt of silver, and the best-in-class manufacturers use about 15 milligrams per watt. So where is the silver? Well, the silver is, of course, in the contact, and we have different technology to consider. PERC is the one that used the less amount of silver. It used silver on the front side to contact the N-type region. The back side use aluminum for contacting. And there is a little bit of silver for the bonding pads. The TOPCon technology use a aluminum silver contact on the front and a pure silver contact at the back. So we have to expect to have in TOPCon a lot more silver usage than PERC. Silicon heterojunction cells use silver contact on both sides. So again, use more silver than TOPCon and more silver than PERC. And for tandem cells, for the future tandem cells like perovskite on silicon, also use pure silver contact on the front and the back. So on the table on the left-hand side, you see the consumption of silver for the different technology. Best in class use roughly about 15 milligrams per watt in the PERC technology, for TOPCon about 25, and for heterojunction about 34 milligrams per watt. At 1 terawatt production level, PERC technology would use 53% of the current global production of silver. TOPCon will use 88%, and HJT would use more than 100% of all the production of silver. So at 1 terawatt level per year, we need to reduce to 5 milligrams per watt. at 2 terawatt or at 3 terawatt, we need to reduce to less than 2 milligrams per watt. Now, indium and bismuth, both are used in heterojunction technology. Indium is used in the cells for the deposition of TCO, of transparent conductive oxide, and it's used in a layer of indium tin oxide. And heterojunction use roughly about 4 to 10 milligrams per watt of indium. So if we want to keep the consumption of indium less than 20% of the world supply, that means that we cannot grow heterojunction to more than 37 or 95, less than 100 gigawatts. So we cannot grow, for the moment, we cannot grow heterojunction technology to more than 100 gigawatt per year. Bismuth is used in the soldering of the contact, the ribbon and the wires to the cell. So during the module assembly, typical consumption of bismuth, and this is because we need low temperature solder. And so we use a tin bismuth alloy. And if we use a 12 bus bar technology, we use typically 7.8 milligrams per watt. If we use a smart wire technology, we use 13 milligrams per watt. So the maximum production in those technologies using bismuth, if we want to stay below 20% of the overall production of bismuth, that means that we cannot grow this technology more than 560 gigawatt in the case of 12 bus bar, or 330 gigawatt in the case of the smart wire technology. So we use quite a bit of material, and the most important one right now for PERC technology. So if we suppose PERC, we at 1 terawatt level, we would use almost 90% of the worldwide production. So 20,000 tons of silver. Of course, there are other materials, copper. We reach about 35% of worldwide production. Glass, about 14%. Aluminum would reach almost 20%. And silicon, we use 32%. But silicon, it's not a scarce material, so it's not really a problem. And it's not a problem for glass either, or for aluminum. It's just we need the industry to grow. The copper could be another problem, because copper is used not only for PV, but also for the inverters and for the EV cars and for the transmission lines, etc. Now, let's talking about recycling. Of course, we need recycling. Today, we have roughly about 100 megawatt of modules to recycle. In 10 years, the volume will be about 10 times larger, about 150,000 tons of module to recycle. When the system is decommissioned, we remove the concrete, we recycle the metals, the steel, the aluminum frame, we recycle the cables, the connectors, etc. The modules are partially disassembled, so we remove the frame, we remove the cables, the J-box, etc. We can remove the back sheet also. So those are easy to recycle. After that, it becomes a little bit more complicated. You could crush the modules and sort the particle to recuperate glass and metals and the different components, or you could use a chemical process or a thermal process or a combination of all of those. Today, we need to recognize that recycle technology is not developed enough. We don't recycle silver. We don't recycle those important metals that we need to recycle. And why we don't do it? It's because the technology to do it is too expensive. So we need to develop a good recycling technology that is good and cost effective to recycle the material that will be the most scarce in the process, like silver, for example, and also bismuth or indium if it's possible. So we arrive at the conclusion of my presentation, and I hope that you find this quite interesting. So PV manufacturing will continue to ramp up, and we need to keep to ramp up to more than 25% growth per year to reach about 3.5 terawatts by 2035, and then stabilize it to reach a cumulative capacity that could reach about 70 terawatt by 2050. There is no issue with the energy payback time and the energy return on investment. We are fine with that. We keep reducing energy and water consumption, as Adele will show you, and we keep reducing our emissions. However, financially, we have to be careful that we cannot grow faster than what is limited by the capex and EBITDA. And right now, fortunately, capex is decreasing by about 50% every 3 years, which is good. But the sales price also is reduced about by the same amount, and the EBITDA of the industry is not very high. It's in the range of 10 to 15%. We have temporary supply constraints, and we have seen that in the past with polysilicon, with glass, with wafers, etc. But those are temporary issues, are not fundamental issues. It's just the supply chain having difficulty to grow as fast as the demand. In terms of material sustainability, we have several issues, particularly silver. We need to reduce silver to less than 2 milligram per watt, and that could be done, but most probably we'll have to switch to copper. Copper plating is probably the best technology to replace silver, and it's in development right now, and hopefully will be in production very soon. Indium, bismuth, cadmium, tellurium basically should not be used for mainstream PV technology. So heterojunction has an issue, a bigger issue than PERC and bigger issue than TOPCon, and we need to find a replacement for TCO. We need to replace indium tin oxide with another material to provide the same conductivity and the same transparency as indium tin oxide. And bismuth needs to be kept as low as usage as low as possible. Recycling will become an important issue. Recycling will become important 10 years down the road. But we need to realize that recycled material will not help the scarcity of those materials until mid-century. Okay, so thank you very much for your attention. I'll be happy to answer your questions.
Thank you very much, Pierre. Pierre Verlinden is the Managing Director of AMROC. Thank you for that presentation. One quick question. We do have quite a lot of questions coming in, and I'll ask you to stick around for the Q&A session. A couple of questions have come in regarding the energy payback time. I think that's slide 11 of your presentation. The numbers that you showed, or 13 of our joint presentation, the numbers that you showed were from 2017, the most recent study, and I think it was multicrystalline technology that was modeled there. I'll go back in the presentation. Is there any update to that? And what kind of impact do you think this switch to monocrystalline that we have seen, and also things like thinner wafers, what kind of impact is that having on the energy payback time for solar?
Well, not so much the thinner wafers, but mostly the diameter of the diamond wire. This has been critical to improve the energy payback time. So basically, I remember about 2004 when I did a study to see how many tons of silicon we need to per megawatt. We needed about 14 tons of silicon per megawatt, and now we're down to about 4 tons of silicon per megawatt. And this is mostly due to the fact that the diameter of the wire to saw the wafers has been reduced from 200 microns to right now less than 50 microns.
Mhm.
And that's been a huge impact for the amount, because we need to realize that the purification and the crystallization of silicon are the most energy demanding step in the fabrication of the wafers. So if we could reduce the kerf loss when we saw the wafers from 200 micron to 50 microns, that is a huge improvement in the energy payback time.
And
so
you would expect the figures then today to be an improvement on what we can see here from the 2017
absolutely
study.
Absolutely. I don't have the exact figure recently, but we less than we in the range of 1 year or less than 1 year for the energy payback time.
Okay.
However, we have to say this is calculated for a good irradiation, a good solar resource, for a panel that is very well placed, that has no shading, etc. If you put the same panels on a building and it's partially shaded in a city with other buildings, you don't get that energy payback time,
Okay.
of course.
Excellent, Pierre Linden. Thank you very much for your time, and please stick around for our Q&A round.
Sure.
Now, moving on, Adele Zhao is the Head of Product Solutions and Marketing with Trina Solar. Adele, thank you very much for presenting today, and I'll pass the floor over to you to give us an insight from a manufacturer perspective onto solar sustainability as we head towards the terawatt age. Over to you, Adele.
Thank you, Jonathan. And thank you for Dr. Pierre's great presentation. So now I'm going to share with you what we have made the progress on sustainability from one of the leader in the solar industry, and also our responsibility as an industry moving forward. So Pierre also mentioned about the global warming earlier. So from Trina's side, as one of the industry member, we see clearly that it's urgent that we have to contribute to lower the temperature increase in the world. So hopefully, with all the efforts together, everyone in the society, we can still hit 1.5, maybe 2 degree increase compared with year 1900, the temperature. This is exactly why this industry exists and why Trina exists. But to make this happen, you cannot work alone. So it's a global effort. So it's a government, it's an industry, it's a society. The good thing is that we're working together. So these are just some examples, like COP21, and soon will be COP26. 27 going to happening soon again. So it's really a collective effort in the society, everyone. In Europe, where I am at the moment, we see a strong demand, for example, also on residential segment this year, that a clearly sign that the society itself is moving. Everyone around us feel the urgency, want to do the energy transition, which is very great, besides the industry itself and also the government policy. So why Trina exists, and this is why. So everything we do is we want to produce solar energy for all. So we know we need much more renewable energy. We need to electrify the world. And for Trina as a company, so our mission is to produce solar energy which is affordable, sustainable for everyone in the world. So this is essential. And clearly, the vision we see is we want to create a net zero future. And how we do that, in Trina's case, we want to deliver smart solar energy solutions. So everything we reinvest in the future is always related to solar, to renewable. So this exactly show in our business lines where we are heading in the future. But how to make this transition in the society, but also within a company. So in Trina's case, it's very important that our top management have a very strong commitment towards sustainability. So in our case, it's Mr. Gao, who is the founder of Trina Solar 25 years ago. He's still the chairman and the CEO of the company, and he is actually the main force with the team, Trina team, together and pushing this sustainability. Sustainability for us in environment, health, safety of also our employee, of the whole supply chain. We have a strong social responsibility towards the whole society. And also every product we produce, we very much care about the product life cycle to make sure we use sustainable material, we reduce our emission along the way. So now I'm going to give you a bit more insights in Trina's case about environment, society, and the product and solutions. So how we make sure we become a sustainable company in the industry. Also, we help the industry itself to transform. So I will start with the environment, which is the most question I got actually in daily work from our clients about environment, because everyone always start about emission, right? What is your carbon footprint, which is the most popular word at the moment in the industry. And this is also why we exist as clean energy industry. So from Trina's side, one side is we measure our emission, also the material we use, etc. And also we have a very clear goals set for the years to come. And this is all public to the whole industry, to the society, and this is our strong commitment. So we used year 2020 as a benchmark. And for 2025, so we only have 3 years to go, actually only 2 years to go, because it's already end of 2022. So we want to further reduce our category 1 and 2 emission by 50%. So these are the energy we buy and we use on our own production side. So we have to continue to push down the energy consumption. One side is use clean energy. Another side is we reduce energy consumption per kilowatt, which is essential. So another thing is, as I mentioned, so we have to reduce our energy consumption. And also, one thing we normally ignore when we talk about environment is about water footprint. So if you look around, you'll notice we actually will have water shortage, actually already happening in many countries. So in the industry itself, during the production, we also use a lot of water. So we have to reduce the water footprint. This is very, very important. So we keep monitoring how much water we use. We also put facility in the site to recycle the water from our own plant. So in 2025, we also target to reduce another 20% reduction of water consumption per megawatt. And for 2030, this is an even more ambitious goal, which we are working on. Number one, we want to use 100% renewable energy for all the operation of Trina. And the second is 3 R's. What does it mean? Reduce, reuse, recycle. This also applies to every person, like everyone here, like your daily life. For a company, it's exactly the same. We have to reduce material consumption, usage. We have to reuse material and recycle the material. So this is our goal for 2030, and we're gonna promise we're gonna have zero waste landfill by 2030. So how to achieve that? We actually set up a dedicated team within the material team to work on recyclable material, and also to think how to recycle as much as material as possible at the end of every module's life. And also, we want to make sure we're gonna produce more energy for the whole world. So the main thing transition happening is definitely in the factory itself. So setting up the goals, but how to make sure happen, right? Within the company, Trina itself, we have 17,000 employees. And then there is a supply chain, and there are a customer on another side. So we have to make sure everyone can work together and transform our production and operation. So we have to put a very strict system into the company, into the factory, to make sure this will happen in the years to come. So that's why we follow ISO system. We also, on top of that, we also measure the whole product life cycle. That means the whole value chain we have to measure. So make sure we can really do the transition we commit to. And here, I think it's not just Trina alone. As a solar company, so we actually, on the downside, we do use a lot of energy. We have a lot of emission, which we try to push down. But on the other side, and our product produce clean energy for the whole society. So in the future, the goal is we push down the emission and we're going to produce more clean energy for the whole society. So here's a number just to show you in the past 6 years, what our emission, and on another side, and how much actually clean energy we produce. You can see the number is already very exciting. We are actually negative. But on the other hand, we know we actually have to help the society, another industry, to decarbonize. So this will be the essential goal we want to achieve in the next years. So in the last years, already passed, we have already delivered over 100 gigawatt modules to the whole world. We also have, our product have produced 135 billion kilowatt hour. So that's very impressive. That's equivalent to 4.43 gorgeous hydropower stations. So that's the biggest hydropower station in China. So that's 4.4 of it. So that's really impressive. I'm pretty sure at the oil industry, we have to work more together and to push more solar into the whole world. And we are also committed. We are part of the science-based target to hit 1.5. So this is a goal we have together, and we're going to continue to push down the emission ourselves and also for the whole world. And then I'm going to move to society. So as a company, so emission is, we have to be lower. Another side is society. So it's a community we live in, we work in. It's our own employees, also our supply chain, and also our customer. So we have to maintain a very healthy society, healthy industry. So the people inside are essential. So we have to be happy in the working in industry. So how we manage our supply chain in particular, we make sure we have full transparency in we audit frequently our suppliers. We also building up an IT system to have traceability in the supply chain. And also one important, we only choose a supplier who are open and willing to work with Trina according to our standards, so they can follow us on transparency and traceability. So this is like the basic criteria we choose the suppliers. But how to make that happen exactly? So same like green factory, we need a system to manage this. So there are three main things we are doing for our own factory and also our supply chain. The first one is we do yearly assessment and management of our suppliers. So we do audit. So the basic thing we do, like quality, cost, delivery, service, like any other ordinary important audit. On top of that, we also measure, for example, another part of on the sustainability, we also audit them. So the second is EHS management. So that's environment, health, and safety. So this is, again, Trina, we do it all the years. And also, we make sure our supplier also do and share the data with Trina. And we also do audit. And the last is they have to, all the suppliers need to also send commitment letters. So they promise they're going to deliver these sustainability criteria to Trina as they're our suppliers. On top of these, our own system in place, we also have hired third party to do the audit. Here is just one example. We use EcoVadis. We already have done in the last 7 years. So we always ask them to audit. So give us an outsider perspective to help us to continue to improve on the ESG. And the last part, I'm going to share with you about products and solution. So Pierre also mentioned earlier, right? Reliability is essential. You don't want to buy a module can only work 1 year, and then the whole industry needs to produce many, many more modules, which require a lot of material, going to have more emission to the world, which is very unhealthy for the earth. So what we do is we make sure we can deliver very high quality, long lifetime solar panels to the industry. So our minimum warranty, performance warranty for every module we deliver is 25 years. And if it's double glass module, so it's more reliable, it's 30 years. And Trina, this year is our 25th anniversary. So you will see a logo 25 next to Trina Solar logo everywhere this year because this is our anniversary. So we are actually already hit the first warranty promise term to the industry. So we are still around, so we can deliver our warranty. We're very confident we're going to be around in the next years to come. So, but how do we make sure we can deliver very high quality products? One side is our own manufacturing. The second side is we do a lot of tests in our own lab and also third party. Here are some very international recognized lab like TÜV and UL. These are the most, I think, recognized in the industry. There are also many more you're very familiar with. So we actually do a lot of tests with them to make sure we have high quality products. But what product we do, test we do exactly. So we actually do beyond industry standard. So if you are a bit technical or you understand how the industry work, these terms should be quite familiar for you. I just take one example. For example, thermal cycle 200. So basically, we do 200 cycles in the thermal in the chamber to test our module to speed up in the real, like to simulate the real environment. Right? It will go minus 40 degree to 85 degree. So in the industry standard, you do 200 cycles. But in Trina's case, we do 400 to 600 cycles of our module to make sure they are fully have really high quality, the material we choose, and also the production line, they really can fulfill these quality requirement. Besides these IEC UL tests, we go beyond. We also do tests outside of IEC and UL standards. Here are some examples. For example, we also do extremely high temperature or high wind load tests. And here we also do an uneven snow load test to make sure the snow, our module can handle the snow like on the roof. And here we have done all the LCA, which is life cycle analysis for all our 210 modules. So here are one is from TÜV Rheinland. So very exciting news. So the best module actually can achieve below 400 grams per watt, which is very exciting. So this is the lowest we hit already, and we're going to continue to push down. So as you can see, all the technology advancement really also help on the sustainability part significantly. So this is a great achievement for Trina, also for the industry. On top of the international LCA standard, we also do, for example, for France, Korea. So some country have slightly different regulation. We always make sure we are compliant with the local requirement on the emission part. We also do EPD with the clients. So this is per kilowatt hour. In this report, one information can share with, this is already done like 2 years ago with last generation of our product. So we could hit 1.4 or below 1.5 year energy payback time. So this includes the whole life cycle of the module in the power plant with the client. So this was also very exciting. And the irradiance wasn't that good in this project, actually. So now, 2 years later, I'm pretty sure this number is much lower. So on top of LCA, we also do full bankability assessment with third party to make sure the whole production line, the financial part of our new products are very bankable. So it's easily, so our client can have access to finance markets. So this is a report we do also. And this is probably not new to the most audience here. So Trina is always on the top of the bankability rating in Bloomberg NEF rating every year. So in the last 7 years. So we're always 100% bankable, which is very essential for our clients. And last, I'm going to show you quickly so what we offer. So today, the majority of our technology, almost 100% this year, Trina all transferred to 210-based technology, which actually also help on the energy, reduce energy consumption in the ingot wafer, which Pierre mentioned, is because of the larger wafer. So this is also very helpful to make the product more sustainable. So for Trina, we actually transfer all our capacity, including new capacity, to the 210 base. So they are Vertex. And we also introduce a new Vertex N series, which is a TopCon product, as we have to work on is to reduce the material consumption like silver. So this is something we're working on. And this product will be ready already in Q1 for mass production. On top of module, what we do is we also offer a tracker to maximize the energy production from both front side and back side. This will also help to reduce the emission for our clients in the power plants. So these technology are essential. So it's not just a module, also the whole system. And another very important thing for the whole industry for renewable to grow further is storage, because renewable is not very stable. Sun doesn't shine 24 hours. In some countries, there are a lot of cloudy days during the day, like UK. So we actually need a lot of storage also into the system to help the grid to absorb more solar and renewable and another renewable energy source. So this is something Trina is also working on, so we can have more clean energy in the world to push the energy transition. So thank you very much.
Well, and thank you very much, Adele Schau, who is the head of product and marketing for Trina Solar Europe. Adele, thank you for that presentation. Just one quick question on the back of it. Does Trina have a take-back network for end-of-life PV modules?
Yes, we do. So we have agreements with some partner to recycle the modules at the end of life. So this is what we offer. So as an option, to be honest, not every customer chooses that option, but we do. And in the future, what we're going to do is, as we know, as also Pierre mentioned, we're going to have 10 times modules recycled in the coming years. So the existing partner probably cannot recycle all the module in the world. So we actually really encourage more company, including Trina ourselves. We're also working on that. So we have the capability in the industry to recycle modules in the future. But it's also very important our clients have more willingness to recycle the modules. So I think it's a whole ecosystem we need to build as an industry to make this happen.
Interesting. Thank you, Adele, for that. Now, Pierre Verlinden, Managing Director of Amrock, I'll invite you to quickly come back. We have come to time, but let's get through a few of these questions. There's quite a lot of questions coming through. Now, Adele, in her presentation, addressed module reliability and extending, more rigorous testing to authenticate module reliability and lifetime. I think it's an interesting point about module lifetime in terms of sustainability over the long term. Pierre, we have one question about that. Can you comment on the methods that are being deployed to improve module lifetime? Do you feel that 40 or 50-year modules lifetimes could be achieved in the future, and how much, what's the role for smart electronics to be embedded in modules to help achieve that?
Okay, well, that's a very good question. First, when people talk about 25-year lifetime or 30-year lifetime, like Adele was talking about, we're talking about the warranty. That doesn't mean that the module will stop working after that. I have installed modules on my roof about 25 years ago, and it's still working fine. There's a little bit of decrease in power, but they're still working, and they could work probably 30 or 35 or maybe 40 years. There's been some example of modules being in the field for more than 30 years. And there's been some studies to show that low degradation is possible for those modules, and the technology has improved tremendously since I started working 40 years ago on PV. So it's we know a lot more about reliability science of photovoltaics today than we used to know 40 years ago. So yes, I believe that module lifetime could go to 40 years. Warranty is another issue, and the problem is warranty is for many of the manufacturers, how could they give a warranty of 30 years, because the science, it's not capable today to say 200 thermal cyclone corresponds to so many years. It's very difficult. Reliability science is very empirical. We keep testing the same way, the same modules, and compare the result with the modules we fabricate 30 or 35 years ago. Can we say today that the module we fabricate today will last 40 years? Nobody can say that right now, but what we know, that's the reliability is increasing, and that's great. And there are some programs like Duramat programs at NREL in US working actively trying to develop science to have modules lasting more than 50 years.
Okay, thank you, Pierre. Adele, can you add in terms of what's being done, from a manufacturer perspective to increase reliability and lifetime?
Yeah, I think I agree with what Pierre said. So warranty is one thing, and in the real life, it's another thing. So actually, our utility customer and also IPP especially, they actually do the modeling based on 40 years lifetime in reality. So this is, in many cases, especially big utility customers, they do want 40 year. Even we only give 30 year for double glass, but they are very confident themselves because they know. We also know, like Pierre said, but so as in reality, they are already doing the financial modeling with 40 year. So this is what I see in the real life, in the real projects. And on the other side, for Trina, what we do is, for example, we do a lot of tests. Also, we are the first one to introduce, like in a match scale, is for double glass. So that actually push up the warranty from 25 to 30, which is very helpful for and that's why we see like all the big clients who want 40 years, they all choose double glass. We don't even have to tell them. They say we want double glass upfront. Yeah. So this is one thing to do. Another thing we do is we make sure we work with the whole value chain, also inverter company, mounting structure company. So to make sure we're very compatible, we can optimize the system so we can work really very well together as a system. This is also very important.
A system approach. Okay, thank you, Adele. Pierre, you mentioned silver consumption, particularly in terms of high efficiency technologies like TOPCon and heterojunction, where there is increased silver consumption. One question saying, given the constraints with silver, are there alternative metals that can be used? You pointed to copper. And what would be the kind of efficiency cost? Will we see an efficiency decline if we turn to alternative metals like copper plating?
Okay, so there are two parts in your question, Jonathan. I see two metal that could replace silver. It could be aluminum or copper. Personally, I think both have a potential to replace silver. The first one that is closer to manufacturing is copper plating, and actually you can improve the efficiency. It's true, copper has a little bit lower conductivity compared to silver, but copper plating, the conductivity of copper plating is closer to the bulk copper conductivity than the screen printing of silver to the bulk conductivity of silver. So basically, you have a benefit with copper for two things. One is you could put narrower lines, narrower fingers with copper plating than with screen printing. So copper plating of 15 or 17 microns copper lines is quite easy compared to silver screen printing. And on top of that, you have a pretty good conductivity after plating compared to the bulk conductivity of copper. So I think it's all beneficial. The whole question is how to integrate copper plating technology with the existing manufacturing and getting the permit to do that, because there's a lot of fear that the effluents from copper plating would create pollutions in the environment. And the other question is reliability, of course. Do we get the same reliability? And there's been some issues with peeling or adhesion problems with copper plating in the past.
So while silver screen printing, the use of a squeegee and a screen print seems a rather kind of primitive technology, it is remarkably effective, and we know it's reliable. So a switch to copper would be is possible, but it is quite a big switch for the industry.
Correct.
Correct. Adele, is Trina looking into copper? Can you give us any insights there?
Yeah, I'm not sure if I can share it. We're definitely looking into these because as you know, Jonathan here, so we are also moving away from the holding need N-type. We know that will come because for high efficiency, but also Pierre mentioned, so there are a lot of silver needed. So how can this material is essential, silver, also like indium for HJT, right? These are the most important topic actually to discuss, because that's not just also material, because a lot of customers look at the financial. When we have material shortage, the price will increase, like silicon. So it will be very difficult to push for energy transition as well. So these are all linked. When the material become less, the price will go up, like silicon. So it's essential. So we are actually looking at all these options. So also we are a bit cautious. What's next thing we're gonna put into the capacity? Because these are the big investment. So we have to choose wisely. And that's why we're working with like Pierre, all the top scientists in the industry to make sure we make the right choice for the industry. So we're very sustainable.
Okay, now very quickly, I'll run through the last couple of questions. Adele, Pierre in his presentation showed the effects that kind of temporary supply chain or rather shortages, bottlenecks in certain materials has constrained the learning curve at certain points. We have a question saying, it seems like the polysilicon supply that's constrained the industry in terms of cost over the last year or so, or 2 years, might be coming to an end. Do you see any supply chain next in the near future? Is that what Trina's seeing? And what will it be?
We do see it will become better next year. So we agree, which is very good news for everyone. So for us, for our clients, for industry. So we do see that it's better. Will be another bottleneck maybe. As company, we try to mitigate this risk to really work very closely with our supplier. Also, for Trina, I think also many other companies will become more vertical integrated ourselves. So we have more control on the upstream on silicon ingot wafers. So also it would be greener. So we put everything together in the one factory. So it's more sustainable. We don't have to transport them around. So these are essential. But silicon we do see will become better next year. We already foresee that.
Okay. Well, that's good news. One last thought then. We've talked a lot about solar. We do have quite a lot of questions about storage. I know energy storage, as we go to terawatt scale, the needs for energy storage are going to scale hugely. Also, Pierre, in your presentation, you had the blue line with materials, these critical materials that we shouldn't be using at very large scale. A number of them are very important for the energy storage, for the battery industry at the moment. Just as a kind of final thought, Pierre, are critical materials and potential shortages an even bigger issue for the battery energy storage sector going forward, or at least with the technology mix that we have at the moment?
No, you're totally right, Jonathan, and that's why it's important that we talk today about sustainability, because we cannot develop technology that are not sustainable. Basically, it's period. We need it. We could do that 10 years ago. We cannot do that anymore. And I'm ringing the alarm signal for a lot of those technologies. No, we have to realize that all the technology will evolve. When PERC will go to copper plating, TOPCon will go to copper plating, heterojunctions will go to copper plating. Probably ITO will be replaced with aluminum dope zinc oxide, so AZO. A lot of people are working on it. It's not sure that we get the same efficiency, but basically that's the roads we are working on. And the same for the battery technologies. And of course, lithium batteries are important these days, but there are a lot of new technologies for storage. Lithium is not the only one. In terms of batteries, people are working on sodium batteries, on salt batteries, and then there are other ways to store energy. You could store thermally, you could store with compressed air, you could store it with pump hydro, etc. There's all kinds of different technologies that the people are working on. I'm not a specialist of all those technologies, so I won't go into there. But sustainability, it's a very important point. Like you mentioned, we cannot afford to develop technologies that are not sustainable at the multi-terawatt level.
Thank you very much, Pierre. Adele, from Trina's perspective, as you mentioned, kind of taking a systems approach that also extends to battery energy storage. How are you addressing sustainability in that regard?
Yeah, I agree with Pierre. So I think for Trina, we always invest into technology, make sure the whole ecosystem of renewable works. So we're definitely going to look into different technology, also on storage, and see what works. At the moment, we are working on mostly in Europe, for example, for utility scale. But we do also see need, like in CNI, in at home, they will have different needs. Maybe we'll need different technology. But we are very open also to work with another technology partner to find the path for everyone. But especially now, I'm also traveling now with meeting customer in different market in Europe. Every customer wants storage. This is amazing. So that's the next thing we have to explore together to find the solution for different type of segments, which is sustainable.
Well, maybe we can explore that in a standalone webinar, energy storage and sustainability. But for now, we have gone over time. So I will draw a line under our discussion today. Adele Chao from Trina Solar, thank you very much. Pierre Verlinden from AMROC, thank you very much for your contribution. And thank you to everyone's great questions. Unfortunately, we couldn't get to them all. Thanks, Adele.
Great, thank you. Our pleasure.
Okay, thank you very much for attending this PV Magazine webinar. As a thank you, we are offering a 10% discount on subscriptions. That cover you can see there is the November edition of PV Magazine, which literally hit the shelves today, just being distributed. So please do subscribe to that and help support us provide these webinars and other great online news. Some of the top news you can see there for free for you. And the November edition has a very strong focus on the finance sector. So solar finance run right through from the VC early stage, right through to projects, PPAs, and even at end of life. Coming up, we've got some great webinars at the end of the week. We're looking at module manufacturing non-conformities, so a focus on module manufacturing. And then next week, a webinar that will be looking at monitoring of PV power plants. So you can see we have webinars all the time covering the entire value chain for the solar PV industry. But until then, it's time for me to thank you very much once again for attending. My name is Jonathan Gifford. This PV Magazine webinar, thanks to Trina Solar for your partnership. And please do fill out that survey at the end. It helps us improve our webinars. Until next time, thanks again.
Thank you. Bye.